Hello, everyone. Welcome to the AI Agents Hackathon live streams.
The AI Agents Hackathon is a free virtual hackathon running from April 8th to April 30th.
We're hosting over 20 live streams where you'll learn how to build agents using various Microsoft technologies. At the end of the 3 weeks, submit your project for a chance to win fantastic prizes.
And now over to our friends at Reactor.
Hi, everyone. Thanks for joining us for the AI Agent Hack. Before we start, I do have some quick housekeeping. Please take a moment to review our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is recorded. It will be available to view on demand within 24 to 48 hours. With that, I'd love to turn it over to our speakers for today. Thanks for joining.
Hey folks, thanks for joining. Thanks again. This is going to be all about building multi-agent AI applications with Semantic Kernel and of course Azure Cosmos DB. My name is Abhishek Gupta. I'm a product manager in the Cosmos DB team at Microsoft, and I'm here with my colleagues Sandeep and Sajitharan. Hey folks. Why don't you go ahead and introduce yourselves? Saj, you're on mute. Sandeep, you too.
Hey everyone, I'm Saji here working on the Cosmos DB product management team, mainly focusing on the developer experience with Azure Cosmos DB and making Cosmos DB as a database for developers.
Awesome.
Hi everyone, I'm Sandeep here. Also work on the Cosmos DB team, and yeah, I help evangelize Cosmos DB, build samples, and that's me.
Awesome. That's very humble, Sandeep. Anyway, all right, cool. With that, let's dive in, and I'm going to quickly share my screen now. Amazing. All right, let's jump in real quick. So what I'm going to do is start off by setting the context real quick, and then we'll move on to the practical stuff and nitty-gritty and deep dive. So there will be a few slides, but I hope you don't mind that, and I really hope this is useful for you. So what are AI agents? Now you will see different definitions for these terms. This term is probably thrown around a bit loosely given the hype, but I think it's helpful to think of the concept of an agent as opposed to an exact definition. So one such observation is from Chip Huon, who is also the author of a very famous book called AI Engineering. And really the essence of AI agents is that they are meant to accomplish tasks, of course. And in order to do that, they work within a predefined environment. They plan a sequence of actions to achieve these tasks, and then they go about executing them using the tools which they have. Now, a lot of the power of AI agents comes from their ability to use these tools to get things done. Now, this could be calling an API or searching the web to get the latest data, or they can use memory and state to get richer context through techniques like retrieval augmented generation or RAG. And to top it all off, agents are great at planning. So they can map out these intricate step-by-step strategies, plans, and also adjust based on feedback. Now that part is very, very important to understand. A great example, at least for me, this is a very biased example, is coding agents like GitHub Copilot or Cursor or Windsurf or whatnot. You might have used them already. And this is one area of applied AI agents that I am personally most excited about. Now, you can think of them as pair programmers or fellow engineers. Their environment essentially is the computer or our laptops. Their actions include navigation, searching, viewing files, and most importantly, editing those files when we ask them to generate code. And they are equipped with the right tools to help them execute these actions at the end of the day. Now, let's consider these common architectures when it comes to building agentic systems. Now, in a single agent system, there is perhaps one large language model or LLM that directly interacts with the bunch of tools it has access to. Now, this approach is fairly straightforward, but it can become a bottleneck when it comes to handling multiple complex tasks and workflows. Now, in contrast, on the right, we have a multi-agent approach, which involves many agents working collaboratively. And often you'll see a higher level supervisor or a planner component that oversees these agents and orchestrates their task delegation and so on and so forth. And you're going to see this in action very soon, but I hope you get the gist here. And the multi-agent approach can be, as you might assume, it is complex to implement, but it is at the same time very flexible as well as scalable. Now, instead of relying on, say, one agent or one set of LLM and tools to juggle everything, you have a bunch of specialized agents to handle your specific tasks and workflows depending upon your application needs. Now, prompts or prompt engineering, as you might know, is important for any generative AI LLM-based application, but even more so for these agentic-based systems and apps that we have. Now, you need to be very, very deliberate and precise when it comes to creating prompts for these agents. So essentially, you start by defining the agent's role. It could be a support agent or a transaction agent, and so on and so forth. So agent's role, its tasks, and also make sure to provide context and step-by-step instructions for specific workflows. It might sound like a lot, but just like any best practice with any prompt engineering for a GenAI app, you need to do that for agentic apps as well. And you should also think about adding examples to help solidify the agent's intended behavior. Anticipate things like edge cases and provide fallback actions like, perhaps in this case, in the case of, say, a transactions agent escalating to a customer support, right? So you can look at that example prompt which we have for a transaction agent. Now, if you notice carefully, if I give you a second or two, which I don't have too much time, but if you read this later on, perhaps, you will notice that there's this implicit thing happening, which is kind of referred to as routing. Okay, so if you look at this diagram here, in this example, there's this agent A that initiates a process, performs a series of actions by calling tools. And if the task requires, say, further specialization, it knows when to escalate or pass on the control to another agent, perhaps agent B. At every decision point, the flow kind of adapts based on the situation. So it could be looping back for additional steps or interacting with different tools, or of course, transitioning to a next agent, right? So the point here is that these agents are not working in isolation, hence the term multi-agent, right? And they function as a coordinated system. Each agent has a clear role, but it's part of a larger system or a decision flow, so to speak, right? And mind you, all of this is easier said than done when it comes to implementation, especially if you try to build all this orchestration, routing, prompting, and all these kind of functionalities from scratch. You're going to find yourself in trouble and sort of doing the things which you're not sort of supposed to, which is building great apps and providing value to your customers. And that is where frameworks generally come in, and same is the case with agentic applications as well, which these frameworks can help with that plumbing and heavy lifting and orchestration. Now, there is no dearth of agent-based frameworks as well. You might have heard of LangChain or LangGraph, Autogen, and so many more. Semantic Kernel is in a similar way. It's an open source, we like to call it enterprise-grade framework, which is available in 3 languages, Python, C#, and Java. So we are going to show you C# today. And it has a lot of different components, as you might assume, with a framework, which can be used individually or together. And this includes common ones like chat completion or embeddings or vector search, and obviously a subcomponent for building agentic applications as well. So let's quickly double click on the components which are specific to the application which we are going to demonstrate today. The obvious one is chat completion, which you can use for building chatbot applications, obviously. But more importantly, what you will see later on is how it serves as that foundation or glue component when it comes to building larger agentic apps as well. And as you might expect, the chat completion component within Semantic Kernel gives you the ability to plug in different model providers as well. And it also includes a very interesting feature called function calling. Now, to be honest, this is very simple conceptually, but a very, very powerful feature. Now, if you recall the word tool from one of my previous slides, function calling is sort of a different name, or perhaps a manifestation of that. Now, what it allows you to do is declare these pieces of logic and let your application invoke it dynamically as part of this agentic workflow. And there is a lot of flexibility that you have in terms of how these are invoked. And you'll see that later as well. And how they are invoked and how they can be grouped together into this concept called plugins, which can then be referenced when defining your sub-agents within a part of your larger agentic application. And when it comes to building the agents themselves, you can obviously use the agent framework. Now, don't get confused, this is a sub-part of the larger semantic kernel framework itself, and it works and gels very well with the rest of the components, such as plugins and chat completion that I just showed you. Now, it has, I can't give you an entire, we have too less time, but I'm just going to touch upon the important notions when it comes to this agent framework and some of its, classes or components, right? Now, it has a notion of an agent thread, and agent chat. Now, all of these are something which you're going to see very soon, but bear in mind that all these core abstractions work with different implementations. So they are quite flexible in a way. So for example, there is an Azure AI agent type that works with or that complements an Azure AI agent thread type, just to give you an example. And when it comes to building multi-agent apps, you can use this abstraction, which is known as agent group chat. Like I said, you'll see many of these things in action very soon, so I'm not going to steal the thunder and let Sandeep take over later on. And continuing on, now, as all of us probably understand at this point, LLMs are very, very smart and powerful, but and all these frameworks make it even easier to tie them into agentic applications. But LLMs don't have the notion of a memory or a state. I mean, they are getting better and better, but memory and state are still something which you'll have to sort of integrate externally. It's a simple request response paradigm, so to speak, when you try to interact with an LLM. And that's the reason why handling different types of states and memory components is very important, especially in the context of agentic apps, which can get complex very fast. And obviously, in this case, we use Azure Cosmos DB to power the multi-agent system that we are going to show you. And I have highlighted here some of the capabilities in green that we are going to demonstrate. So this includes the usual goodness that Cosmos DB is known for, which is being schemaless, multi-tenant, low latency. But in the context of AI applications, it is the ability to store chat history objects for your conversations, having a vector store for your semantic search. So essentially, it's about using Azure Cosmos DB across the entire spectrum of use cases when it comes to building generative AI applications. And like I said, this is not just about chat history, but also about retrieval augmented generation. It's about semantic caching. And of course, like I said, agentic app development as well. And customers are already using Cosmos DB extensively. Now, before I wrap up and pass it on to Saji, there's one more thing I want to highlight. So in Azure Cosmos DB, you can choose the type of vector index. And one of those types is based on a technology called DiskKNN. Now, the interesting bit about DiskKNN is this, it's not just one isolated thing. It's in fact an entire suite of vector indexing algorithms, which was initially developed at Microsoft Research to power vector search at enormous scales. And it is already being used internally at Microsoft. This includes Bing Multimedia Search, M365, SharePoint, and even local semantic search within Windows 11. And for the first time ever, when Microsoft released DiskKNN, it was built into Azure Cosmos DB as a database engine. And this is, again, like I said, not just limited to providing large-scale vector search for our customers, but it is also these other good things like low latency, cost efficiency, and high throughput, which Cosmos DB can deliver thanks to DiskKNN. So I really, really encourage you to read this white paper, which is very, very approachable, by the way, and dive deeper into DiskKNN. With that, I'm going to pass it on to Saji.
Hey, thanks, Abhishek. Thanks for setting up the context. So Abhishek has given you the brief idea about Cosmos DB and also agent concepts. With that in mind, let me show a quick demo of the multi-agent app for a banking scenario and we will dive into details as we progress. So let me log into this app using myself as a user, and then I have a tenant fabricant in this case. Once I log in, I will be able to see the chat history on the left side navigation panel. And let me start a conversation with as a user to understand some of these things, right? So let me start with this question about who can help me here. As you could see, there is a response from the agent coordinator with my name popped up, and also it asked me the question, how it could help me, right? So I will go ahead and pass the prompt saying that transfer $50 to my friend. In this case, you can see the response, like it asked me back saying that what is the phone number and the email address for that particular contact. And also you can see the agent in this case is transactions. So let me go ahead and provide these details so that I can get the transactions successful. Yeah. So there are two accounts available in this case with some balance. So it asked me back saying, okay, which one I need to choose. So I can pass in this case Platinum card. Okay, it goes through this certain path and it identifies, okay, it doesn't support direct money transfer function, and it asks me back with certain questions. So probably I can go with that path, but let me go ahead and show another scenario of, say, if I need to look for a savings account with highest interest rate. All right, I got back the response with the agent sales with some information. So as you could see, based on the prompt that I make, it is able to transfer or route the request to particular agents, and then you can see those responses. Assume if you want to see how this is happening behind the scenes, you can always check this debug icon, which shows how it's selecting those agents and also how it's making the decision to terminate and transfer back to some other agent. So Sandeep will talk you through the implementation of this particular scenario. And also you can see some of the features, like it automatically summarizes based on the context that I have provided in this chat. And also you can see there are certain features that it supports. You can rename according to the way you need and so on. And again, this is multi-tenant user scenario, so you can log in with multiple users and so on. That's kind of the overall demo that I wanted to show. With that, let me navigate back to slides to talk about some of the things that I demonstrated, right? That's sort of a demo, but if you would like to understand the flow in this particular diagram, the system is designed to mimic how a real banking task could be handled efficiently through multiple AI agents. At the top, you can see a user who interacts with the system. Think of a customer, myself, using chatbot or a chat assistant. The user requests are first handled through the coordinator agent. This agent acts as a smart traffic controller. It understands the user's intent, and also it delegates the task back to the right agent. And as you could see, there were three specialized agents that we had in the demo. One is sales agent, support agent, and then transaction agent. So each of these agents handles specific tasks. For example, sales agent handles all the onboarding and loan related tasks. It uses tools like get offer information and so on, create account and so on. And then support agent deals with service related request. It can submit service request. It can get branch locations. It helps the users with specific customer support needs. And then we have the transaction agents. As the name indicates, it does all the transaction tasks, such as bank transfer, transaction history, or bank balance checks, and so on. So this is kind of the overall flow that I showed in the demonstration. If I navigate back to deployment architecture, let me walk you through the deployment architecture of a multi-agent banking app. In this case, starting from the left, you could see we have certain developer tooling listed. One is the Azure Development CLI, and then GitHub, and also we have the VS Code. So you can run it in local and then make the changes, use GitHub actions, use GitHub to manage your source control, and then you can also use code spaces in order to do the development workflow. GitHub handles the source code, source control, and CI/CD, and then CLI simplifies the Azure resource provisioning part, and then VS Code acts as a way to or go to ID in this case to build either on Python or any language that you prefer. At the front end, we have the Angular app, which is hosted on app service. This is what, as a user, I could see on the front end to interact with. It's a UI layer that talks to the backend, which is a C# API, enabling the real-time transaction of the responses that you see on the front end. Our backend is implemented using .NET, which acts as an orchestration layer. It interfaces with multiple components, as Abhishek explained in the previous slides. First, it integrates with Semantic Kernel. That is our intelligence engine. It leverages prompt engineering, memory, and planner capabilities to support some of the multi-agent workflows that I demonstrated. The .NET layer communicates with some of the model that we use, and also text embedding model in this case for a natural language understanding and generating the contextual responses that you could see in the responses. And in terms of storing the data, as Abhishek mentioned, we are using some of the capabilities of Cosmos DB, starting with vector store. And the other capability in terms of multi-tenant scenario is the hierarchical partitioning, which lets the users to scale according to the way they need. So you don't get to the limit of 20 GB logical partitioning. You can have hierarchical partition key defines for tenant, user, and so on. So this avoids the way to limit data, so you can scale accordingly in terms of how many chat history that you want to store and so on. All the data processing is funneled through the chat service layer, which ensures that agent responses are appropriately routed and contextualized before hitting the client interface. On the data side, as I mentioned, it powered by the Cosmos DB, and in terms of some of the other integrated services, we are using application insights in order to track some of the traces that happens from the front end to back end. And also we are using Azure RBAC to control user permissions and also secure access management. That's sort of the overall deployment architecture. Now you must be curious about how to implement this in C#. I will hand over to Sandeep to show you how to build end-to-end.
Thank you, Saji. Thank you, Abhishek. Yeah, so I have the difficult job of walking you through the code, but I'll try to make it as simple as possible, and I'll try to demystify the complexities here and try to do it through a step-by-step approach that we're going to do. So what we're going to do is, instead of directly jumping and creating a multi-agent chat, we will start with something very basic, which is an hard-coded response. Then we'll convert that hard-coded response to an agent response, which is, so the difference between the two is, when you say hard-coded response, it is basically a static string that is getting sent back. There's no LLM, there is no AI there. Then we convert that to an AI and send that response through an agent. And then we move to the next step of converting that hard-coded response to something which is more dynamic, so that we can select an agent and then the response can changes depending on the agent. And it also helps, gives us a way to test the different agents one by one. And then finally, we move to the multi-agent chat, which is our final destination, where we have this multiple agents orchestrated in a way that they all talk to each other. They together try to solve the problem and build the solution. So with that, let me take you through the project structure or the solution structure. So the solution basically consists of 4 projects. The banking services project, which has got all the business logic that are related to the banking operations. So you can call it all the CRUD operations of the bank, which is about creating a service ticket, doing a transaction, fetching a user account, and anything else. So all the the core business logic resides in the banking service. The chat API, which is the .NET API, web API that we are going to use, which is what the front end application talks to. And then comes the chat infrastructure. This is the core place where all the AI stuff is happening. This is where what we are going to focus on. And then finally, a common project which has got some helper classes and some models which are used by all the other projects. So let me dive into the chat infrastructure project and see what are the components. So I've done blow up of that. And here there are again multiple files, but we are interested in 5 files primarily. The semantic kernel service is the one that is going to have all the semantic kernel related stuff. The chat service is the one that interacts with the API. So all the API calls come to chat service, which eventually invokes the semantic kernel to do the job. And the semantic kernel will internally use the chat factory to build the chat and the agents and the prompts, etc. So that's the basic structure of our project. So let's start with our basic code and then start moving up the chain. So this is the first function, which is the hard-coded response. So as you see, there is a function in the chat service which says get chat completion async, which passes the tenant ID, user ID, session ID, and the prompts. Again, because we are having a multi-tenant system, all the calls pass the tenant ID, user ID, and session ID so that we can use the hierarchical partition key here, as Saji had mentioned. So the apart from these information which is provided from the front end, the user prompt is the value that the user provides. So the text box entry that the user provides is the user prompt. And what we are doing here is we are just generating a message object, and we are replying a hard-coded value, which is say replay user message and plus whatever user message. So that's where you get a hard-coded reply. There is no LLM here. There's no AI here. This is simple C# code. So now the next step is we want to make this AI enabled. We want an LLM to respond to it. So let's move to that step. So before we move there, let's just talk about how the message model looks like. So the message model has got, again, the session ID, tenant ID, user ID. It are the 3 keys that are going to use for the partition key. It has got an ID, which is a unique ID. Some messages may have a debug log, some may not. So debug log is basically used to get the debugger information based on the bug. When you click on the bug icon, we use the debug ID to go and get the debug information from the database. There's a type, there's an author, and there's an author role. So when you say author, it basically could be a user or an agent. So the message object is used by both the message that is sent by the user and the reply that we get from the agent. So depending on who the sender is, the author will either be user or the agent, and the author role will be the transaction agents, the sales agent, the coordinator agent, or the customer support agent, depending on the agent that you are interacting with. Of course, text content is the value or the text that the message contains, and timestamp is when that message was created. So when we talk about a session is basically a series of messages where all of them have, where the session ID is common and where it is sorted by the timestamp. So now that we understand how the whole chat thing looks like, what is the basic model that we are going to follow, let's delve into how to convert this hard-coded response that we saw in the previous slide to something that an LLM can generate. So before we do that, I thought we should move this code into semantic kernel so that we kind of focus all our LLM code in a separate class. So we now go on creating a class called semantic kernel service, and then we create a get response method inside it and use that to generate the response. So let's move there. So here we have the get response method inside the semantic kernel service, And what we are doing here is we are building a basic agent and using the agent to get a response. So the simplest agent here, we're calling it a basic agent. We are giving it an instruction to say greet the user and translate the request to French. And we are giving it a kernel, and we are basically just cloning the semantic kernel and giving it a kernel. So these are the three pieces of information that we're giving to the agent. And then when we say agent.invoke async, depending on the prompt that the user has given, it will use that message, this user message that's here, and it is going to generate a response, and that response will be added to the completion messages here. Now, in this case, as you would expect, if I say hello, it will also say hello, and it will translate my hello to French. Again, very simple, but LLM based response. So that's my next level of complexity, where we are using a semantic kernel here. We are using an agent here to start responding using an agent. Now, next step is to make it a little more complex so that we can make it dynamic. We can have it more like a conversation. So as you saw in the previous slide, there was no history attached to it. And Abhishek mentioned this in his slides too. An LLM is a stateless. No, when you interact with an LLM, it is stateless, which basically means it doesn't know who you are. It doesn't remember what you said and any of those things. So you have to tell it everything that you need for context so that it can respond accordingly. So that's what we do by using the history object. So when we say history object, an history object is all the messages that have been uh, conversed in the past. We put it into the chat history array and pass it to the LLM. And then when we pass our next prompt, then the history is used as context, and then the LLM gives us a response. So in this case, we used Cosmos DB, get the message history object from Cosmos DB, and then we build the message history object whenever we are going to invoke the LLM, and then we call it. So now by doing this, we are building history into it. Next thing that we have done is we are now, instead of hard coding an agent, we want the agent to be dynamic in nature. We want the agent to also, so you could use the same code for building different agents. So what I do is instead of giving hard coded values here, we get those values from some function calls. So we have a system prompt.get agent name, a system prompt factory.get agent prompts, etc., which generates the same kind of value. So here also, if you see the name is, it's just returning some value and it's returning a hardcode text. So by doing this, we have kind of now moved to the next level, which is saying, okay, my agent is getting created, but it is not hard coded. It's calling a function and getting the value. But you may say, oh, but what I can, you see, this value is still hard coded. Yes, you're right. It is. We are moving to the next step where we will remove that hard coding also. And that brings us to this concept of prompty files. So prompty files are nothing but text files with the extension .prompty, and these contain all the prompts that we want to store, all the text that we want to store. And prompts are the basic building block for LLMs. This is how you give the LLM instructions on what to do, what not to do. So what we do is we create a bunch of prompty files for different agents, for different purposes. We store it on disk, and then we load those prompty files, and that way we make our agent dynamic. So for the purpose of this workshop, you will see the prompty files are stored along with the web API project. It is published along with the code, but a best practice says that do not include your prompty files inside your code, because you should be able to modify your prompt without really need to do a code deployment. So maybe a good suggestion is to store your prompts in the database itself, or store it in a blob store or something, so that you can change the prompts without changing the code. So now that we have a prompt, we can now load these prompts dynamically. So now the same function that we had, which was saying get agent prompts, which was returning a hard-coded value, now can return a prompt from the prompty file based on the parameter that is passed. So that's how we are making our code more dynamic in nature. Another thing that we did here is to say that we don't want to repeat all the common rules. So we said we'll store the agent specific rules in the agent specific prompty files, and we will have a common agent rules.prompty, and we will embed we will we will add those common agent rules to each prompt response from this file. So that way, what you get when you say get agent prompts is actually a combination of the specific agent plus the common agent rules. So now we are good, but what we now did is we are now using the agent type here, and we passing an agent type also. And when we pass this agent type, it uses the build agent function, and it gets you the prompty files, which we did already. It gets the agent name. And one more thing that has happened is instead of we were earlier, if you remember, we were just cloning the semantic kernel, but now we are returning and we're calling a function to get the kernel. Why are we doing that? This is being done because we want our agent to also have access to tools. So if you just clone the semantic kernel, there are no tools that are available to the agent. So we want the agent to have access to some tools, and that is why we are, instead of just cloning it, we are generating an agent, creating a kernel where we first clone it and then we add plugins to it. So again, depending on the agent type, you will load a plugin here. And what is a plugin? How does the plugin look like? Good question. That's what we are going to look at next. So all that we are doing here is based on agent type. We're cloning the agent, cloning the kernel, and then doing kernel.plugins.add from object and passing a library here, which is sales plugin or transaction plugin, depending on the agent type. So let's look at what a plugin looks like. So a plugin is a regular C# code. The only thing that is different here is it has got attributes that have been added so that it can be called a plugin. So we have a kernel functional attribute, which has got a meaningful name, which is used by the LLM to understand what you are doing. A description that again explains what this function is doing. And if required, you can also add attributes to the, you can also attach attributes to the parameters. Now remember that when we, in semantic kernel, when we talk about plugins or function calling, we are not going to describe these functions. We are not writing any code to say which function to call, when to call, etc. The LLM goes through the metadata, which is the attributes that you have added, the parameter names, and the data type, and it tries to make sense out of it, and it automatically makes this call. So naming your functions, naming your parameters is important. So if your functions are random names, or if they're not having good spelling issues, or if they're grammatically not correct, it can make a difference. So spend some time trying to review your function names, at least the public function names, and make sure that they make sense so that the LLM can make good use of them. So we have this plugin. We are able to now clone the plugin, clone the kernel, attach it, and create a plugin also. So now you are kind of ready with a system where there are multiple agents available, but at this point you are passing the agent type as a hard-coded value. So you are saying my agent type is going to be coordinator, or my agent type is going to be transaction, etc. So you still have not reached a stage where you are multiple agents that are orchestrated to work together. You have multiple agents, but they each have to be invoked separately, independently. So some of the prompts that you could try is, if you say coordinator, the prompt is, if you say hi, it will greet you, it will tell you welcome you, etc. If you are a transaction agent, and if you ask it how much did I spend on groceries, then it may look at your transactions and give you a good detail of your grocery transactions. Similarly, for the sales agent will be good at suggest looking at all the offers or the new products that are available and suggesting you which product is going to be best fit for you. And the customer support may be able to, let's say, file a complaint for you or look up for an existing complaint and see what is the status for that. So each of these agents has got different roles because they have different plugins, they have different prompts. But at this point, you are still running a single agent at a point in time. So the next thing that we want to do is make it a multi-agent chat. We want to bring in some bit of orchestration into it. So let's get into the next level of complexity. So before we get into that level, there is this question that the LLM has: which agent does what? Which agent will get invoked when? Will multiple agents be talking together, and when will an agent stop responding to a user prompt? So these are important things that we need to help the LLM with, so that we have a good experience. Otherwise, it's going to be like a room where multiple people are chatting, but you're not getting anywhere because there's no engagement rule. There's no, everybody's chatting, everybody's giving you some messages, but there's no clarity to the discussion. So we want to bring in some rules on how these agents are going to behave. That's where the concept of selection strategy comes in. So when there are 4 agents and each of them have got their own specific role, and I put in a message, what should happen? Should all the agents start coming and talking to me, or should one agent come and talk to me? I would like one agent to come and talk to me. So we need to tell the LLM on what are the different agents that are available and what are the rules that they can use to select an agent. So for example, so these rules are telling the LLM that first of all, there are 4 agents, so you need to select from these 4 agents. Second thing is, read the user's request and route it to an appropriate agent. Second thing is, if a user is responding to an agent, then the same agent should come back and take the transaction forward. It should not be a user, let's say a transaction agent asked me a question, I gave a response to the agent, and suddenly the sales agent comes back and starts to respond to it. It's not going to be a good experience. So we want the same agent to continue the transaction till it reaches a logical stage. Also, if there is some kind of clarity problem, then you go back to the coordinator agent. So this is again a prompt file. It is a text file. We are just putting the steps here. So again, prompts are not only used to define the scope of an agent, but it's also used to define the strategy. A similar strategy is called the termination strategy. So termination strategy is more about when to stop. So if I ask a question, should the agent give me one response followed by another response followed by another response, or should it stop after giving some meaningful response? So we want to make sure that there's this when there's no, it's not becoming a chatterbox kind of scenario where somebody puts a question and suddenly there's a huge number of responses that come in. We want only meaningful responses to come, and we want only very small amount of responses to come so that it becomes a good experience. So a termination strategy is designing when should the LLM decide that no further participation by an agent is required. That's the main decision here. So again, we are giving some prompts here to decide what we want. What we really want is the LLM to say yes or no, just 2 words. Now, and this is basically to say whether you should continue or not, right? And we're giving prompts so that it decides what to do. So now that we have written these 2 strategies, how do we use it? So we want to use it in our code. We want to use it in our C# code. And when you talk about C# code, we use structured objects. We use classes, we use JSON or whatever, but we need some structure to it. The LLM response typically is natural language. So if an LLM starts responding in the natural language, it's going to be very difficult for you to parse that natural language and figure out what the agent said. It can, and that can be the natural language responses can be in many forms. So it's going to become very, very difficult for you to make sense out of it. So what we want here is we want to force the LLM to respond to some scenarios in a structured way, which basically means I want the LLM to respond using a JSON schema. So here I have defining a JSON schema, and I'm also telling what are the different properties, what are the data type for it, and what should you store in this object. So I have, for example, two JSON schemas here. One is the continuation schema, and another is the termination schema. And these schemas are actually used to define what is the continuation the output of the continuation strategy and the output of the termination strategy. And these two, you would, so if you remember, Sajid during his demo was showing the debug log. When you click on it, it was able to show the reason of why the LLM thought that the sales agent was the right agent to respond, and what was the reason, what is the condition that the LLM thought that it was enough, that the sales agent single response was enough, or further responses are required. So the termination strategy. So now here, by providing a JSON schema, we are forcing the LLM to respond using a JSON format. So we now have a strategy which is in natural language. We now have a schema of the JSON object that we want. And what we do here is we now build an agent group chat, which is where what we are doing is we are trying to bring all the agents together and start responding. So instead of passing one agent type, if you see here, we're creating an agent group chat and adding all the agents that we have. So we are adding all the agents, but there's an interesting thing, which is the execution setting. And this is where we provide all the strategy of termination and continuation. So let's look into that and see what we are doing. So here we are calling the get strategy function. In this case, this will go and read the prompt file for the strategy, for the selection strategy, and it will get you the prompt file, and this is going to get you the JSON schema. So by doing these two, what we are going to do is we are now forcing the LLM to respond in a structured format based on the prompts that are provided here. So if you see here, when the LLM responds, the result object can be deserialized, and you can get it into a continuation info object, which is now a C# object, and I can store that in a very in a structured manner in C#, and I now can even do other operations with it. So what we did here is we used an LLM response, but we converted that into JSON object so that we can use it in the C# code. So what we are doing here is every time the LLM is invoked, it selects an agent, we log that information, or we store that information so that we can go back and look at it later and understand how the LLM is behaving, why is it doing certain things. This is important because if you don't do this, what you may see is you write your prompt with the best intent and the best English that you have, but yet the LLM is doing something different. It could be because there is a conflicting prompt, or there is some kind of understanding gap, because of which the LLM always does something wrong. But by using the selection strategy and the termination strategy debug information, you will know what did the LLMs look at, why did the LLM decide to do something in a certain way, and then you will be able to take corrective action. So now we have this is how you do the selection strategy. Similarly, we have the termination strategy, and we now put it all together, and we have the final get response function, which is where we have the chat history, we reading the history and adding the history to it, and then we invoke the group chat, and we pass the user prompt, and then we get the messages, and then the debug informations are also stored into Cosmos DB along with the session objects and the message objects, so that we have everything as a part of the session, and we can through the UI pull up all this information and paint the nice interface. So that's a quick overview of the code. Now, one thing that I would like to do is, because we have very short time, there was no easy way for me to walk you through the code. But what you could do is go to our repo. In the repo, we have a start branch. Go to the start branch and then start following the instructions that have been given. And step by step, it will take you and guide you, and you will reach the end, which is what we have in the main branch. So if you want to look at the code for the solution, then the final code for the solution, then you can go and check the main branch. But if you really want to go step by step, just like what I try to do, and learn how to do it, then you can start with the start branch, and then you can follow the instructions and take it to the final step. So with that, I think I have completed my code walkthrough part. So Abhishek, I'd like you to come up and take up the closing part.
Sure thing. Thanks, Sandeep. This is awesome. Very comprehensive. All right, cool. So just to recap, and we have a bunch of questions. I'm going to get to that real quick, right? But just to give you a few final thoughts. So essentially, using all these frameworks for agentic app dev definitely helps with the heavy lifting, as you might have realized, seeing the swaths of code which you'll have to write, and obviously you need help there. But even with a framework, you need to make sure that the structure and configuration of your agents, I mean, you do that properly depending on your workflows, the prompts and the strategies and so on and so forth, right? This was obviously specific to Semantic Kernel. And when it comes to the backend database, well, you never know. And of course, you would hope that your agent app becomes the next big thing. And if you use Azure Cosmos DB from the very beginning, not only will you be ready to handle the scale, but it'll probably be the only data store that you will need to worry about, thanks to its versatility in the terms of the workloads it can handle, right? So with that said, I want to make sure that we do justice to the questions as well, which I see a bunch of them popped in. By the way, if you saw someone by the name Vihan Chills in the chat and you don't know who that crazy guy is, that's me. And that's my son's handle who kind of switched things around on my YouTube account, by the way. So sorry if that caused confusion. But yeah, we can take a few questions. And I'm going to, and I know Saji, you dropped in with a few inputs here. So let me scroll up here real quick. There was a question on SignalR, which Saji, you think you meant you already answered. On consistency levels, Saji, you took that as well. So there's a question from Nishant, and he asks, when we talk of specialized agents, what does it mean? An agent has access to a specific database and can perform specific functions. So I'll take that, and Sandeep, Saji, feel free to chime in. So a specialized agent is mostly about your domain problem, your domain application, your workflow, right? That's how you would sort of slice and dice your agents. And depending upon that, you would implement it. And depending on that, you would see what resources or what databases or whatever it is that it needs access to, excuse me. So the notion of a specialized agent is really tied to your application requirements, as opposed to accessing something. That's more of an implementation detail, if that makes sense, Nishant. Feel free to chime in, Saji.
So I just want to, I just want to add something to it. So I think Abhishek touched upon that point when he slide. When you why multiple agent and why not single agent? What happens is, and again, this is not just to agent. I think this is true to human beings. We have this whole concept of departments and job roles in even human life. We are primarily to solve the problem, because what happens is, if one person is going to do everything or one department is going to do everything, it becomes a total mess, because too many things to do, and there's confusion, and there is no clarity on what has to do, what has to be done. That's exactly the problem with agents also. So if you put all your business logic into one agent, what you may see is that one rule conflicts with the second rule, and then it becomes very difficult to manage. Second thing, you may not, again, from a data source perspective, some tools may be reading SharePoint, some tools may be requiring a database, some may be just searching the web, etc. Now, you don't want everything to be done by a single agent and make that whole thing so complex to. So what you can do is you can create agents based on, let's say, one what kind of data they're accessing, to what kind of job they are doing, and give it a very, very, just like when we say, when you create a job role, you have to have a job description. Similarly, here also think of it the same way. Define what your agent is going to do, what is his description, and focus on that. If you're doing something outside that, then maybe it's time to create a new agent and give it a description rather than trying to put everything into one, because then again you will create the same problem. So keep your jobs very clearly demarcated.
Yeah, and I think there's this point about microservices, right? So agents are, I mean, and this is purely my take, right? Don't quote me on it. Like this microservices of the AI app world, so to speak, right? So you can make them as specialized as you want to, or perhaps a little broader. So it really depends upon your requirements and your implementation at the end of the day. Just like microservices, right? You can keep chopping up and make them as nano functions or whatnot. So I guess the same applies to agents as well. And there was a question around GitHub repo and everything. There have been many short links which have been dropped, but I'm going to do that again just to make sure if I'm unable to post for some reason. Maybe yes, we see it here. Thanks. So that's one. I saw another good question from Nishant. Why should I use Azure Cosmos DB to store my vector embeddings instead of Azure AI side? This is a tough one, and I am going to be a bit biased, and I cannot give you a complete answer in a minute's time frame. It's a tough one, right? So essentially, I'll give you a very, very high level overview, right? So think about this term, perhaps real-time AI, right? Say the application which you just saw, or perhaps an e-commerce, or very, very latency sensitive chatbot application with very high concurrency, which involves operational data as well as the semantic search specific data, and they go hand in hand, your transactional data and other sorts of data, right? I think your vectors and app data, whenever there's a use case where they want to live together and you don't want to mess with different data stores, Cosmos DB will be a good fit. And again, like I said, all the other goodness added, low latency, high throughput, cost effectiveness of disk gain, and so on and so forth, right? But AI search, and again, like I said, I'll be honest, slightly biased but honest, but if you have like searching multimodal enterprise content, like images and documents and videos, you obviously want to explore Azure AI search and see if it fits your need there, right? And I'm going to pop in a link real quick here, and folks, any one of you can share, but because I am unable to for some reason, I think this is fairly good guidance. It should come up on the screen real quick. I think that can help guide some of the decisions if you're trying to choose the right vector search for your applications. We still have a little bit of time. So let me, and feel free, Saji or Sandeep, if you want to pick specific questions, that's perfectly cool. In case I miss. So I saw a question from Wagner Mello. Can I test a chatbot locally using the bot framework emulator? So to be very honest, I don't have too much context about the bot emulator framework, but I think what Saji answered, and I'm going to second that, is the Azure Cosmos DB emulator. You can test these things, the AI agent app and other things, using the Azure Cosmos DB emulator, run it locally on your machine. And yes, you can definitely do that, but I'm not sure about the bot emulator framework which you mentioned. So just to make that clear, Wagner. I hope that helps.
What you can do is Semantic Kernel works with Olama, so you could actually install Olama on your workstation or your and then deploy a Phi model or any other model, and then Semantic Kernel should be able to function with that too. Of course, the performance, the quality, etc., would depend on how much resources you have, what is the model, etc. But yeah, so if you just want to build something, it's possible to do locally.
Yeah, I guess there's multiple things to think about. What Sandeep just touched upon was the model itself. You want to run them locally, and the other part is the Cosmos DB piece, where you can run the Cosmos DB emulator locally, combine both these components, and you have a nice agentic app running locally which you can play around with. So I hope that helps. Anything else, folks? We have, I guess, one more question, maybe. Let me scroll. I believe this code is on GitHub. Yes, it is. I'm looking into Python, but C# is critical. That's good to know. I hope this helped. Do we have a separate kernel for each agent? I actually answered this, but I wasn't sure. It's flexible, right, Sandeep, Saji? I mean, it depends upon how
it's flexible. So the thing is, you can have this, like, so if you remember the first slide, we were having just cloning the existing agent, semantic kernel.clone. So we just cloning the existing kernel and using the same kernel. So in that case, all the agents are sharing the same kernel technically. But in the second case, we were also cloning it, but customizing it by adding in plugins. So the idea here is that each agent has got its own kernel, it has got its own plugin, and that way it can behave differently from other agents. So yeah, if you want to have function calling, then yes, you need to customize the kernel for each agent separately. Otherwise, you can clone it.
Awesome, thanks, Sandeep. One more, because I think this is a very relevant question, and thanks, Nishant. You're popping up really good ones. Sandeep, I'll let you take this one. So we delegate the selection strategy to the LLM, or the LLM being used by the coordinator agent?
So what we do here is, in this multi-agent chat thing, we have the agents. Each agent has got its own prompt file, which tells us what it is supposed to do and what it is not supposed to do. So in the multi-agent chat, semantic kernel multi-agent chat automatically brings the orchestration piece into the picture, where depending on the question, it selects an agent. Now the problem here is, so I am not going to give it instructions to say which agent to select for what strategy, for what purpose. It has each agent has got its own purpose or the job role defined in the prompty file. Now, depending on what prompt I provide, the LLM is trying to make sense out of it and saying, okay, this will be best served by agent X, whatever that agent is.
Yeah.
So I am not going and describing it, or I don't even have the powers to go do that. That will be done based on each of the agent. That's the beauty of this multi-agent chat. What I am just doing in the last code was making sure that I'm able to store that information, that agent selection logic, in a debug file, so that if I see that the agent selection is wrong, I at least come to know what did the LLM think, or what is the root cause of a wrong selection, so that I can correct my prompt. So I fix my prompt to make sure the selection is right. The other thing was just done to figure out, oh, what did you think? What were you thinking when you make that choice? I don't have that. In the absence of that, it becomes completely, like a black box. The LLM is just doing something and I have no clue, and I don't know how to fix it. So some bit of the code, the last bit of the code where we're talking about the selection strategy, the termination strategy, the JSON schema, they are not required to be done. But if you don't do it, what you will see is you have a system that sometimes works, sometimes doesn't work, and you do not have a clue on why it does certain things in a certain way. So for making a solution predictable, to get some debug information to make it correct, that will help.
Yeah, this is very helpful. So this is adding some more context to that, right? Especially about the thinking and reasoning aspect. So if you've been playing around with LLMs, like more and more LLMs nowadays, like you send a chat message, you can click on that thinking box somewhere, in the UI, and say, like, and really dive into what the LLM is thinking. So Sandeep, what he has done is surfaced similar functionality in a custom way in this, banking agent application. So I think it is very, very, valuable for you to go into sort of the nitty-gritties of what's happening. And on that note, there's another question, and I'll take two more questions, just FYI, folks, because I think it's important. I think Nishant asked about testing all of this, and it is like, how do we unit test and package everything, right? And that's a tough question. I have a very partial answer to that, and it might be like, which is, as you might all have heard of, is building evaluations for your applications. Now with agent apps, it becomes even more complex, because you'll have to think about perhaps evaluating your router agent, and you'll have to sort of build evaluations for other components of your application, and so on and so forth. So but yes, one of the answers which I have, and I don't have a definitive one, is to really depend heavily on evaluations, just like you would do with your traditional LLM, much simpler LLM applications. So evals are important. If you don't have anything else but evals, I think you should be good. But I don't know if you have any other takes, Sandeep or Saji. Feel free. That's just my restricted take.
Two things that I would like to add here is one, test your independent model, independent agents to make sure that they're getting the right response. So I'm not talking about the multi-agent thing. Just make sure that your single agent at any point in time is responding and doing the things right first. So first level of testing is that to get sure your agent is behaving as expected, and then the next step is the multi-agent thing and bringing it together. Now, one more thing to watch out, and actually this is coming from my real life experience and burning my fingers, is when you make changes to your prompts, test your stuff very thoroughly. You may have just removed a comma, but that removing a comma can make a hell lot of difference in the way the LLM interpreted your sentence and how it behaves. So making a small grammatical or a spelling change in the prompt file can make a big difference in how the response is going to be. So you do a search and replace, global search and replace, or comma replace. Unlike C# code, this is not going to throw you a compilation error. It is going to throw you some serious errors at runtime, and you will not know from where it came.
Yeah. So it's all about eval.
Coming from Sandeep's real experience.
Yeah. Oh my, yes. We all know. Seen that, right? Awesome. Thanks for sharing that, Sandeep. I'm sure people appreciate it. And there's one more. And this is, I'm sorry, folks, we are already over time, but this is a very important and interesting question. This is from Nikunj Banker. Thanks, Nikunj, for this thoughtful question. And it goes like this. With respect to context, the session ID and conversation ID should be similar or should be different while doing conversations with various chats, similar to chat conversations with ChatGPT. I think Sandeep, I don't want to put you on the spot, but
no, that's okay.
Data modeling perspective.
Yeah, so a conversation again. I think in our UI we are calling it the conversation, but in the background, in the code we are calling it the session. So it's actually the same. The conversation ID and the session ID are the same thing. But yes, what we do in Cosmos DB is we store all the session information, the messages that are there in the session, and the debug logs that are there in the messages, all in the same partition key. They all share the same partition key, so that when we retrieve the data, it is very easy. It is, and also any kind of update that happens, it can be done through a transactional batch kind of thing. So yes, storing all this information, having similar keys is important for you to get high, making sure that your system scales very nicely and you are able to not hit this 20 GB limit, and you're able to get the maximum out of Cosmos DB.
Yeah, essentially it's a data modeling problem there. So yeah, I hope this helped. Again, Sandeep is talking from practical experience, and also Saji touched upon the modeling around how we use hierarchical partitioning keys in some cases to help there as well, right? I think that's all we'll take in terms of questions, unless Sandeep and Saji, you disagree. Let me know. I want to be respectful of everyone's time. So I think we are good to wrap up. Thank you so much again for listening to us patiently, for your engagement. We really, really appreciate that. And
thanks, everyone.
Thank you.
Yeah.
Thank you.
Cheers.
Hi, everyone. Hope you enjoyed today's session. If you aren't registered for the AI Agents Hackathon yet, register now at aka.ms/agentshack and start hacking on the agent of your dreams.
And if you have any questions along the way, just post in our GitHub discussion forum or attend our live office hours in Discord. And of course, make sure that you keep attending the live streams to keep learning about agents.
Once your project is ready, submit it before April 30th at 11:59 p.m. PT to be eligible for our prizes. Thanks for joining.